In the last lesson, we saw that two elements produce an array factor of 2 cosine of psi over 2, where psi equals k d cosine theta plus beta. That simple factor already gave us beam steering, but real systems use many more elements. The natural question is, what happens to the array factor when we extend the same idea to n identical elements in a row? Line up n identical elements along the z-axis, equally spaced by distance d. Feed each element with the same amplitude, but with a progressive phase shift. Element number n carries a phase of n-1 times beta. The total array factor is the sum of n phasors, each offset by psi equals kd cosine theta plus beta. This geometric series has a well-known closed form. Summing the geometric series gives the n-element array factor. Sine of n psi over 2 divided by sine of psi over 2. When psi approaches 0, both sine terms vanish, and the ratio approaches n, which is the main beam peak. This single formula replaces the two-element cosine and carries all the beam shaping information for any number of elements. Compare the array factor for 2, 4, and 8 elements. With 2 elements, the main lobe is broad. Double to 4, and the lobe narrows noticeably. Double again to 8, and the beam becomes a sharp pencil. The half-power beam width shrinks roughly as 1 over n, so doubling the number of elements halves the beam width. This is the fundamental trade-off. More elements mean a narrower beam, but also a larger and more expensive array. In 3 dimensions, an 8-element broadside array produces a narrow disk of radiation perpendicular to the array axis. The main beam is flanked by smaller side lobes. These side lobes are an unavoidable consequence of the finite array size. The first side lobe sits about 13.3 decibels below the main beam peak for a uniformly weighted array. Reducing side lobes requires tapering the element amplitudes, which widens the main beam slightly. Another classic engineering trade-off. Side lobes are not the only complication. If the element spacing d exceeds 1 wavelength, the denominator sine of psi over 2 can hit 0 again at a new angle, creating a grating lobe as strong as the main beam. Grating lobes are usually unacceptable because they send power in an unintended direction. The standard rule to avoid them is to keep the spacing below 1 wavelength, d less than lambda. For most practical broadside arrays, the spacing is set to lambda over 2. The n-element uniform linear array adds 3 insights beyond the 2-element case. First, the array factor becomes sine of n psi over 2 divided by sine of psi over 2. Second, the beam width narrows as 1 over n, so more elements produce a sharper beam. Third, side lobes and grating lobes appear and must be managed through amplitude tapering and spacing constraints. We now have the complete array factor toolkit, from a single element through 2-element steering to n-element beam shaping. The next step is to apply these tools to concrete problems, calculating beam widths, plotting array factors for specific configurations, and checking directivity. That is where worked examples come in.